Okay, well, thank you very much for this invitation. Those of you who've seen presentations by people from stat agencies in the U.S. will be familiar with the first line of this disclaimer slide. And I will point out that the second line was conducted by me on these results, but that's probably okay. A lot of this work was supported by the National Science Foundation, by the Sloan Foundation, and by the Census Bureau before I had my appointment. Is that the right direction? Yes. Okay. So, in order to motivate why I'm going to talk about some of the things I'm going to talk about today, I want to first give you a vision of how I think about modernizing the way a statistical agency goes about its business, and anonymization, privacy preservation, and record linkage fit into the various boxes in a very well understood way in the traditional outline. So here's essentially the workflow chart. Is that the pointer? Yes, this is the workflow chart for your basic statistical agency. So you have the bread and butter activity, frame construction and maintenance. This is all about lists, and a lot of the record linkage techniques that we were talking about yesterday are about maintaining the quality of these lists and transforming them over time so they can be used to produce accurate sample surveys. And then the bread and butter of the 20th century, sampling from these lists, and then the sorts of things that you learn about in survey methodology classes, how to edit, impute, and do the other post-collection activities. I included over here in sampling all the field work that I know absolutely nothing about how to do, and so I just lump it over in there, and we won't talk about it any further. I only know how to work with things that are bits, not things that are atoms. So at this point, we usually do whatever input data confidentiality protection is done. Where I work, that's swapping and some replacement of the input data with other values, but mostly it's swapping. Okay. Then we generate a preliminary publication data. Publication data are generally tables, but they also might be public use microsamples. Apply another set of confidentiality protections to the output, release the official statistical products, and then post-publication curate some components of this workflow for future reuse. Accurate enough? Yeah. Okay. So I like to have a modeled context for this thing. So I like to think about this somewhat differently. So sitting out here in the space where methodologists live, so that's a lot of the people in this room, we have a process model which consists of relationships between everything unobservable that describes the world like a physicist describes the world when they're doing the math that underlies the particle theory. So this process model says the things that we think we would like to observe or measure on their natural time scale, in their natural spatial scale, and with whatever other attributes they have that we're interested in. All right? And this lives up here as a guiding way of conducting business. And then we take the process model, which describes hyperpopulations, and instantiate it with a finite population, and all the things that we did with frame management live here. And then we develop a measurement model. So the measurement model describes how we're going to sample, how we're going to do edits, imputations, and all of that activity lives here. And then we describe a protection model. So this is where you put a formal set of confidentiality protections on it. You define what you mean by confidentiality protection and how you're going to implement it mathematically, and that lives here. All right. So in my world, that generates a posterior predictive distribution. In other people's worlds, it'll generate a probability distribution function that you might give another name to, but we can all be friends about that. All right. So we now have here the tool for generating publication microdata if we're going to do that, which is the posterior predictive distribution. And these aren't really hierarchical in this sense. This should probably be parallel. We also have a distribution for the entities that we want to put in the publication tables. All right, and so the publication tabular data will live here. And remember that these things have already been protected. So what we're doing here uses the features of the confidentiality protection model, of the formal privacy model, to ensure that once this has been applied, the rest of these steps are safe. Okay? Publication reuse is here. And if the publication reuse involves revisiting any of these first three steps and passing through the formal privacy model again, then the update is here. So it's not really linear like this. Just excuse my not wanting to draw a really nice flow chart. I hope you won't penalize me too much for that. But the point is that each of these, the process model, the measurement model, and the protection model, they describe mathematical manipulations of the data that we can then use to establish the properties of what's been published as microdata and what's been published as tabular data. And we can allow recomputations as long as we loop back through. All right, so that's just to guide my thinking. I've given variations of this talk at lots of different places, and most of the time I only spend a little bit of time on the confidentiality and privacy protection. But there's going to be four principles that I think modern official statisticians, so that's the category I want to put myself in. You get to decide whether, once I've described the set, I'm a member of it or not. Should follow four principles. First is we need to do science on the confidential data. So to the maximum extent possible, you want to do estimation and inference on the original confidential data. Notice I didn't say that you want to let everyone see the original confidential data. You want to do things that were computed off the original confidential data. In my view, this is where current SDL methods egregiously fail their clients. Jerry did two that we can just harp on here. Suppression is known to create non-ignorable missing data. The suppression rule can't be ignorable because why did you suppress that cell? You suppressed that cell because it had information in it that you didn't want to publish. So you have to be able to at least describe enough about the suppression rule so that the non-ignorable feature of the missing data can be accounted for in the analysis. I don't know of a single statistical agency that publishes that kind of description of its suppression rules, never mind the complementary suppression rules. In almost all the other cases, we keep all of the key parameters that you need to know in order to correct the inference confidential, because there would be almost no security if those parameters were put in the public domain. And some of them, not Jerry's colleagues, but Adams, where'd Adam go? Adams' colleagues at Penn State have actually worked on recovering the swapping rates from the published data only. So I don't know, because I deliberately put presentation onto this thing so it wouldn't do anything screwy up there while I was talking enough. If it goes out again, we'll turn presentation. Yeah, okay. I deliberately left my Surface at home. Okay, so we were here, and I think I've made all the points. So just for those of you who are interested, at the invitation of economists, so it's written in social science language, I wrote with Ian Schmuddy a very long paper elaborating on all the sins of statistical disclosure limitation. If you want the math, they did allow me to put the math in an online appendix, so that's the second URL. Well, I assume that you're going to archive these, and you do have permission to archive this, even though you don't have permission to archive my voice yet. Okay, so the math is in there, and the math shows how to combine the process model, the measurement model, and the confidentiality protection model to correct the inference, and it has some very important examples in it of how those inference corrections matter. Okay? So I'm going to sing the praises of two related inference valid SDL methods today. One is synthetic data with validation, and Jerry talked about synthetic data with verification, which is a related concept. And the other is privacy-preserving data analysis of a specific form where there's an end-to-end privacy guarantee that covers the entire system. My view is that these are the scalable long-term components of modern SDL. there's also, at least in the interim, going to have to be much more extensive access via enclaves and other restricted access systems. If you've run any such networks, the Census Bureau's network is in the part of the Census Bureau that I'm the Associate Director for, so I guess I now run one, but I was a user of it for 18 years before I was the titularly in charge. They don't scale. They're at least not the way we do them in the US. I've seen some others in the UK and in France that are much more scalable. So you did hear somebody say that the published data in the future are not going to look like the published data that you're used to working with. And I have already been extensively working inside the Census Bureau to start modifying the procedures that we're using. All right. So the next principle is to respect a privacy loss budget. My deepest regret in the entire differential privacy literature as an economist is that the language that Adam and Cynthia and the other DP experts in this room use is so amenable to economic analysis, but it hasn't been a part of the way they talk about it. I'm going to make it a part of the way I talk about it all the time. The epsilon that you've been seeing for the last day and a half, that is a privacy loss budget. You can't let any more information out the door than that epsilon guarantees it. With epsilon delta, you can make some mistakes at the rate delta, but that's a budget. It's a budget in exactly the sense economists mean a budget. It's not a dollar budget, it's an information budget. But it's the information budget that matters here. We were funded by the public in order to publish data. We have to respect the information budget because we were constrained by the public not to just publish the data. It would be a whole lot easier, and in some places it is a whole lot easier because that constraint doesn't exist. So you run a census, you strip the obvious identifiers off of it, and you put the microdata in the public domain. That's what they do in France because the laws don't require them to protect the confidentiality against a reverse engineer. Have at it if you like. So, epsilon delta differential privacy is a privacy loss budget, but it's actually more than that. It's a technology that describes the trade-off between data quality, published data quality, and privacy loss exactly the way two public good technologies are described in standard economic analysis. And so my value added today is going to be to teach you that, and the rest of the examples they're just gravy if I get to them, all right? So, respecting a privacy loss budget means I have to be able to quantify the privacy loss. And it has to hold for the ensemble of the publications that are done from the underlying confidential data. Okay, so I'm going to do randomized response so that the survey statisticians in the room will recognize what I'm doing. And Adam did it yesterday so that the computer scientists would recognize what he was doing. All right, so in randomized response, I'm going to use the two-question variant. So in the two-question variant, the surveyor has a basket of questions. They're all sealed in identical envelopes. And when I do live demonstrations of this, I take that basket of envelopes and I toss it up into the air, scatter them out on the ground, and get them out. They were then plausibly randomized. So I don't know what question is in each side of those envelopes. If I pick up one of those envelopes, I have no better idea than you what question's inside there. It's either a sensitive question, SQ, or it's a non-sensitive called innocuous question. And if you're concerned about the answer of the innocuous question being potentially re-identifiable, you can have a random set of innocuous questions, all of which have the same probability of a yes answer. Okay? So, what's the privacy loss in randomized response? The privacy loss is associated with the maximum Bayes factor. So the Bayes factor is the ratio of the posterior odds on the sensitive answer yes versus the sensitive answer no, conditional on the survey answer yes, to the prior odds of the sensitive state being yes versus no, okay? Which is exactly equal to this calculation. What's the probability of seeing a yes given that the sensitive question was yes? What's the probability of seeing yes given that the sensitive question was a no? That's 1/2 plus 1/4 divided by 1/4 equals 3 in the case where you ask the sensitive question with probability 1/2, and the answer to the non-sensitive question is yes with probability 1/2. So for those of you, this is a whole lot easier for me to calculate than the way Adam did, but it's the same answer. Differential privacy gets its privacy loss budget from bounding the Bayes factor and then taking the logarithm, because these algorithms compose logarithmically. So the maximum Bayes factor for this differentially private data protection exercise is log 3, or 1.1, now and forever. So it respects the privacy loss budget. It'll also satisfy the other two, the numbers 3 and 4, when we get to them. What does this mean? Well, in order to tell you what it means, I can't just talk about the privacy loss budget. I've got to talk about the data quality. So what would the data quality be if I didn't do randomized response? And let's suppose I'm going to ask a question that I'm going to be able to get a truthful answer to, either because I compelled it, like it's on an income tax form, or for some other reason. So we're not using randomized response to get the people to tell the truth. We're using randomized response to illustrate how privacy-preserving data analysis works. So the sampling precision, the inverse of the variance, is proportional to a factor that depends only on the probability that I ask the sensitive question and the probability that the innocuous question has a yes answer, and nothing else. It doesn't depend on the data. I can therefore define the relative sampling precision as the sampling precision I get out of randomized response relative to what I would have gotten out of non-randomized response, i.e. I ask the sensitive question all the time. Okay? In this example case, where the privacy loss is log 3, the relative sampling precision is 25% of the most accurate estimator. All right, so the variance is inflated by a factor of 4. Okay? That's just a mathematical relationship, exactly the same thing that let me figure out that the maximum Bayes factor was 3, lets me figure out that the relative precision of my estimator is 25% of the relative precision of the original estimator. Okay? So now, what can I do? Change the slide, maybe. Oh, that's right, this doesn't work, but it does work as a pointer. Some of you have seen me do this before. Preach the preacher. So, in economics, this is called the production possibility frontier. On the x-axis is the public bad of privacy loss. It's a bad. So where do you want to be? You want to be here, no privacy loss. As the privacy loss increases, this is epsilon of epsilon differential privacy. It's the maximum log Bayes factor. Okay? The public good is data quality. It's on the y-axis. This is a good, so we want to be up here. What's the most accurate we can get? Well, this is a relative precision, so the most accurate we can get is to reproduce the survey estimate without any randomized response. So this thing is a production possibility frontier. There's at least one other person in the room trained enough in economics to see that there's some increasing returns in this PPF. Ignore that. It doesn't matter for what I'm going to say here. And in fact, in things like private multiplicative weights, it doesn't occur. You get a fully concave PPF. All right. In statistics, SDL in particular, this is usually called the risk utility curve. I'm going to put the risk on the x-axis, and I hate this word, utility on the y-axis, and my utility measure is the relative precision. It's the same curve. Okay. In forecasting, this is just the receiver operating characteristics curve. So the bad outcome is privacy loss. The good outcome is precision of the estimate. In all cases, this northwest corner is the most preferred point, but this frontier constrains where you can get. Every privacy-preserving data analysis technique that you have seen described in the last day and a half has one of these, and myself and various co-authors have worked them out, and other people have worked them out as well. So these are the essential economics of SDL as a technology. Right? So a properly designed SDL technique needs to operate on that privacy loss data quality frontier. Right? If you're inside it, you're wasting something, either wasting some of the privacy loss or you're wasting some of the data quality. If you're outside of it, you've worked a miracle because it's a technological constraint, and that's what technological constraints say, okay? All right, but they're all exactly the same thing, and they don't say a single word about what the best point is on that technology. Describing a technology is not about choosing an optimum. All right. So, how did this literature develop? Well, it developed with the computer scientists down here, saying marginal social cost equals marginal social benefit with relatively small values of epsilon. They didn't say it explicitly, and Cynthia, to her credit, in 2008 said, well, I can't really tell you what the right epsilon is, it's a matter of social choice. But using arguments of revealed preference, most of the computer scientists that I have encountered act like they believe that marginal social cost equals marginal social benefit down here. And if you don't, I'm not trying to malign you. I think this is a legitimate place to think that the outcome is without any data. Virtually all official statisticians and most social scientists act as if marginal social cost equals marginal social benefit way up here with much more accurate data and a lot more privacy loss. So that's just pedantics. That's just me saying, well, I observe the levels of epsilon that are in some papers are down here and in some papers are up here, is my way of saying how you revealed what you thought the trade-off should be. But this is a really well-posed scientific problem because the marginal social benefit from increasing data quality can be estimated by estimating the sum of all of the citizens' willingness to pay for increased data quality with increased privacy loss. Those are meaningful technical terms in the measurement of preferences, all right? And so as it turns out, they can be estimated from survey data, and we have done that, and the reference is on this slide. We were using a different privacy model, so I had to do some translation of the parameters. So in the model that we're using to represent social preferences, the indifference curves, the ISO utility surfaces of the social welfare function are lines. That just makes them easier to work with, okay? And what the slope of this line tells you is what the survey data says people are willing to pay in privacy loss to get increased data accuracy. Now, I'll be frank with you. That's a hard concept to do survey questions on for general social data. So in the paper, which is referenced, the nature of those survey questions are, do you feel the government can protect the privacy of the confidentiality of your data? Answer 1 to 5 on a Likert scale about how much you agree with that. Do you feel that good data are necessary for good policy decisions? Answer 1 to 5 on a Likert scale, how much you agree with that. And then a lot of mathematical modeling to get that into the utility function. But in attempts to design questions that explicitly ask about the trade-off between data quality and privacy loss, it works much better to go into the medical domain. In the medical domain, you can actually get people to reveal in their survey answers that they understand that if there's no cooperation with letting data into the medical database, the diagnoses and treatment plans that come out of the subsequent modeling will be inferior, and that they will benefit from the higher quality medical analysis if they and some others let their data in. So they understand the trade-off much better for medical data. I think we should use that to our advantage. We should try to make our problems sound more like medical data so that we can articulate where the benefits come from the data accuracy. But this line was actually estimated off questions asked on the Gallup overnight poll that the Census Bureau buys a couple questions on every night. And I'll be happy to go into more detail during the open question and answers session if you want. What does this say? Oops, sorry. I want to.
Question. Like the social cost doesn't necessarily accrue to the same people that the social benefit does.
Well, it's a public. They're both public goods. So.
But are you thinking of like allowing?
Yes. In fact, your name is on the paper that proves that this one is a public good, although you neglected to mention that in the paper.
but I think there we were thinking of allowing payments because the privacy cost.
Yeah, but it didn't matter that you were allowing payments or not. What matters is that when you're all done, there's only one price that matters, and it applies to the entire population. That's because once you've set this level of protection, you can't let anybody slip out of it. That everybody either gets that level of protection or better, and that's what made it a non-rival public good. Okay, so the paper that we're discussing in code here is one that Aaron wrote with my colleague Arpita Ghosh, that shows how to construct a Vickery-Clark's Grove auction to determine this surface for a different privacy protection mechanism. I don't want to talk about that today, but that's material here. Okay? So if you solve for that tangency point, then the survey data suggest, that's a good, I think, weasel of that you should ask the sensitive question about 92% of the time, call it 90% of the time, and then you'll be publishing data that have accuracy about 85% of the best accuracy you could attain. So if you believe people's responses to they trust the government to protect confidentiality and they understand that the government needs good data in order to make good decisions, then you will err on the side of more accuracy and its associated privacy loss. If you think that those are wildly optimistic estimates of the marginal social benefit, then you'll go farther down and you'll have less accurate data published and more privacy loss protection. Less privacy loss, more privacy protection. Okay? All right. So that's a single, completely worked out example of why the privacy-preserving data analysis satisfies the budget constraint. It also satisfies the other two things I'll talk about in a second. How you construct the technology and how you make the social choice about which level of data quality and privacy loss to actually implement. Okay. So my third and fourth desirable characteristics of modern SDL systems come straight out of the formal privacy literature. You have to be able to prove that the privacy loss budget was respected. That's English for the algorithms that you use to publish the data have to compose. They either have to compose in parallel, which means that you can use the same privacy budget because you ask two disjoint subsets of the population, or they have to compose additively, which means you've asked questions of an overlapping part of the population. But in any event, when you're all done, you have to be able to say how much of the privacy loss budget you spent, and you can't do that if your algorithms don't compose. So we are now restricting our attention to algorithms that you can measure the amount of privacy loss that's associated with each and add them up or appropriately compose them, okay? And all of these algorithms taken together can't exhaust your privacy loss budget. Here's the hardest one. The algorithms have to be resistant to all future attacks. The problem with current SDL, at least the way it's implemented where I work, is that it's only resistant to the attacks that you're able to simulate inside the laboratory with the data that you're able to acquire today. So that constrains you to the simulations that you're able to run, record linkage experiments mostly, and to the data that you can get today, even if you can get all of the data that might have worked. And so the thing you want to think about are the kinds of surveys that were designed a decade ago, the kinds of products that have become available since those surveys were designed that might compromise the confidentiality protections that were applied to them. So the world changed. I think this has been mentioned several times now, and I'm an adherent of that. Modern SDL methods were designed in the situation where big data was inside the firewall. Outside the firewall was a data-starved population that was grateful for whatever we managed to squeak through the firewall and bless them with. And we managed to push a lot through the firewall because it was a data-starved population. The roles are completely reversed now. There's no statistical agency that I know of that really has big data inside the firewall. A census of population in the US is a couple of 100 million records. And that's round-off error relative to the number of searches generated on any of the major search engines in a few minutes. So the big data are outside the firewall. The computational power is outside the firewall in spades if you work in a severely restricted statistical agency. The algorithms are public, so the methods that one might use to re-identify cases in tables or microdata are all public, and there's a lot of credit in computer science given to getting a new one and to getting your name on Kobe Nassim's slide that he now has in 12-point font, which is every known successful attack on the claim of anonymization by a prominent anonymizer. we don't have one on that list, and I'm not going to say anything that would incite one of ours to get on there. So it's what we're doing now isn't tenable. And so to make it tenable, we're going to have to change. And we might not be able to satisfy all four of those propositions simultaneously and right now. But mostly what we need now is better engineering as opposed to more math. By engineering, I mean the design team and the implementation team being joined at the hip long enough to get all of the principles from the formal privacy model embodied in the actual calculations, and then to have rigorous external review of what you've done so that you can actually credibly say to the outside world, bring in auditors and check this. This is what it's supposed to do, and you should be able to verify that. Okay, so my first example is on the map for employer data. So I'm always delighted to take credit for using differential privacy on the map when we first implemented the residential address protection system back in 2008. The team was led by Johannes Gurke, who was at that time at Cornell and is now at Microsoft. And the two young computer scientists working on it were Ashwin Mashanabala, who's at Duke, he's Jerry's colleague, and Dan Kiefer, who's at Penn State, he is Adam's colleague. But again, I don't see Adam. But
Adam has flown back.
Sorry?
He's on his way home.
Oh, that's right. He was talking about that. We were talking about the privacy minister from Canada yesterday, who I went to a conference in New Zealand in the mid-2000s, and the privacy minister from Canada, who had just caused StatsCan to destroy their linked database, flew from Canada to New Zealand, gave a 1-hour talk. You were there, I think. Gave a 1-hour talk, and then took no questions and got on the plane and flew back. So Adam was here longer than that, and he did take questions, lots of them. Okay, so for this, but we only did the formal privacy model on the residential side of on the map. So even though the residential addresses appear to be resolved to the block level on the published files, they're not really resolved to the block level. They're synthesized from data that was sampled from a differentially private model for the block level residences, and that's what you're actually using are those synthetic data, okay? What we wanted to do is we wanted to finish the work and make something that was formally private for the employer side of the problem. Because on the employer side of the problem, we currently use input noise diffusion, input noise distortion, whatever you want to call it, a system that I also had a hand in inventing, so I'm critiquing some of my own work as well. All right, so this is the graphic. So on this side are reports about where people work, and on this side are reports about where people live who work over here. Okay, so this is the workplace control, and this is the residence of all the people who work over here in Lower Manhattan. Right. This side is differentially private. This side still uses ad hoc SDL methods. Right. So what would we try to do? We tried to develop a system that could answer marginal queries about the characteristics of the workplace, the age, the race, the sex of the employees in a particular workplace. The public characteristic is the geographic location of the workplace. The Census Bureau does not consider the physical location of an employer workplace to be confidential, but all the characteristics of the employment, including the total count, are confidential, so they have to be protected. With provable privacy guarantees for the people, jobs, and provable privacy guarantees for the workplace, which means that the privacy model's got to apply to the individual is in or out, and the establishment is in or out. And it's that the establishment in or out that causes the problem. All right. And we would like the new algorithms to perform comparably to the old algorithms in terms of their data quality. I mean, if they can't, they can't, but if we can tune the parameters and then replace the current publication system with a new publication system that has approximately the same data quality, then we have basically implemented the trade-off that was implicit in the original publication assumptions. All right. I'm not going to show you the math. That's not my comparative advantage. The paper's still in preparation, so I don't even have co-author permission to display the most intricate parts of it. but I will show you some of the results that I know have already stood up. So we're protecting the privacy of the businesses.
Can I go, I want to, can I get the answer to a question on the previous slide?
Yep.
Can you go here? So you said the location of the establishment is not confidential. That's not considered confidential.
Correct.
But its existence, in or out.
No, sorry. There's two different agencies. I gave you the Census Bureau publication rule, which is that the location of an employer business is not confidential because the employee has to be told where to report to work. So that's public information.
Fine.
The IRS, the existence of a business as opposed to an establishment in IRS data is confidential because they are not allowed to disclose whether that business conformed to the tax laws or not,
Right.
i.e. file the tax return. Okay? So there's a material difference there.
Yeah, thank you.
All right. So the privacy parameter here is epsilon. The formal privacy model is not indistinguishability whether a particular establishment is in or out of the database. So neighboring databases don't differ by one establishment. Neighboring databases differ along a percentage variation of the size of the establishment. So two small establishments are epsilon indistinguishable, epsilon differentially private in this blowfish extension. Two large establishments are epsilon differentially private on this blowfish extension, but you can always tell the difference between the local McDonald's and the Ford final assembly plant, okay? So, but in every other sense, interpret epsilon like the epsilon of differential privacy. How close together two neighboring establishments need to be considered in neighboring databases is controlled by this alpha parameter. So really tight would be 0.01. That means that I'm only keeping employment confidential to within plus or minus 1%. All right. Loose is 0.2. I'm keeping it confidential to within plus or minus 20%. So that gives you the bound on how close two establishments have to be before this epsilon privacy guarantee applies. I should say that the epsilon guarantee applies absolutely and in the usual differential privacy sense to all the jobs or individuals that are in the database. So all the people get epsilon in the usual way. All the businesses get epsilon relative to this alpha parameter, okay? So the neighboring databases are within 1%, 5%, 10%, 15%, 20%. All right. And the L1 error ratio is the ratio of the L1 error in the current protection system in the denominator and the L1 error in this new protection system in the numerator. So when it's less than 1, I keep trying to get a line across here on this, but I haven't gotten one. When it's less than 1, the new system is better than the old system. When it's greater than 1, the new system is not as good as the old system, and this is a logarithmic scale, so up here it's a lot worse. All right. So two of the algorithms are difficult to make comparable. So log Laplace is the usual Laplace system applied to the logarithm of employment. Smooth Laplace is a variant that also has a failure rate delta that's being controlled. And smooth gamma is another variant. These are not worth the investment time to show you exactly. What matters is that we are probably going to implement this one, the smooth Laplace, and we have our choice of alphas all the way out, I would argue, even to 0.2 to be relatively close to the accuracy that we were publishing before, with epsilons that are within the range of socially acceptable epsilons if you buy into my social model of what's an acceptable rate of privacy loss. All right. Another way you can think about evaluating this is you can take a particular subpopulation, in this case 30 to 39-year-old women with a college degree, and ask how correlated is the ranking of how many such women there are in metropolitan areas using the old system and the new system. So the top panel is when the place size is less than 100, and as you can see, they're not particularly correlated, although when you let the privacy parameter get big enough, you can get them pretty close. And for large, but not when they're giant, they're all 1. But when they're sort of medium-sized places, this smooth Laplace is just as good as what we were already doing. And at values of epsilon between 2 and 4, the other two are also reasonable. So this behaves reasonably. There's just going to be a lot of noise in these rankings. And truth be known, there's a lot of noise in the ranking using the old publication system too. It's just that the old publication system doesn't have any privacy protection at the level of the characteristics within the employment, because ratios of the characteristics have some problems that are discussed in the paper. Okay, so I just wanted to show you that you can do this. You can now, so when this is implemented, all parts of the on-the-map publication system will be formally private. I didn't say differentially private because it's not exactly the differential privacy model. But the first one took 3 years to engineer. The second one took 3 years to engineer. Basically, we don't have that much time. We need a lot more attention being paid to how to do this in ways that can be engineered and implemented relatively quickly. Okay. So, Jerry told you a lot about the synthetic business data that were developed. I'm going to show you the synthetic data from the Survey of Income and Program Participation. When you get the slides on the workshop's webpage, that's a live link to the explanation. Anyone in the world can access these synthetic data. Anyone in the world can submit a properly constituted analysis from these synthetic data for validation on the original confidential data. That validation is then passed through traditional disclosure limitation. So you're only going to get a few coefficients and their measures of significance, or I'll show you in a second. We got one, the non-parametric regression. Forward-looking, these prototype early systems we're looking to replace with end-to-end formally private ones. So even the validation will pass through a formal privacy filter. Jerry's sitting over there worrying because he's the lead scientist on the application to the ACS. And I am now describing the charge to that group, or I will in the last example. Okay? So I don't have time to talk about this in a lot of detail, but if you want to ask questions about it, you can. The Survey of Income and Program Participation is run approximately every 4 or 5 years as a panel, and there's a wide array of questions asked about income transfer program participation and lots of other things, health insurance. There are about 400,000 households in this consolidated group of 8 SIP panels. Data from tax information filings, so that's W-2s if you've ever worked in the U.S., have been attached, and it's the whole history of them from 1978 to 2012. Data from what's known as the master beneficiary record, that's back into the early 70s, all of the application and awards of national social insurance. So your application for an awarding of a pension, supplemental insurance, disability insurance, and not just the award dates, but the actual payments that went out. That sequence was integrated in. All of these data are in the underlying confidential database. They were all integrated using validated Social Security numbers, so there's no probabilistic record linking involved here. And what's known as the gold standard file, that's kind of not a good name, but it is the consolidated, harmonized set of SIP panels from 1984 through 2008 with the linked IRS SSA data all combined. Okay. Validation is performed on the completed gold standard. All right. Just to give you some idea of the level of how this is done, who's married to whom is preserved, so you know your characteristic and your spouse's characteristics, and in the next version you know some things about the children as well. There's a panel variable, so you can condition the analysis on if you only want to use the 1984 panel or the 2008 panel. All right. The administrative data have been edited for some kinds of inconsistencies between IRS and SSA. The best one is a really funny story, but it takes 10 minutes to tell, and I don't have that time, so ask me later if you want to learn about the birth date story. The latest version has the same basic structure. It has the administrative data updated through 2012, 2011 for the tax return data. It has the universe of panels that the Census Bureau curates on the SIP. The 2012 panel can't be added yet because it's not complete. It has monthly benefit data directly from the SIP. It has virtually all of the dates of application, dates of award variables synthesized within it. You'll see why that matters in a second. It has a weight, so even though one of the advantages of these is they could have been resampled, so you didn't need to use the weight, it wasn't resampled, so the weight is now provided. And an improved fertility history. It also has user-requested variables from version 5. So users did analyses and requested additional variables, and they were added to the synthetic data. All right. There's the system for handling the missing data. So the missing data are all imputed using multiple imputation with 4 implicates. And then the synthetic data are generated as 4 implicates of each of the 4 multiply imputed implicates. And the formulas that Jerry published in 2004, I think in survey methodology, are the correct combining formulas. Okay? Gender and link to your spouse is never synthesized. Everything else is synthetic. Okay. I checked, somebody asked me, there are 16 implicates. I'm not sure where the rumor that there wouldn't be came from. There are 16 implicates. They're all housed on a server dedicated to serving up analyses of these data. Anybody can use them. If you do the analysis according to the rules, which you'll have to read on that page that is linked here, you can then submit it for validation. Right? So, why might you want to submit it for validation? Well, probably some of you saw this. The American Statistical Association published an official editorial on the appropriate use of p-values, which brings to the front some of the issues that Cynthia was talking about, and that we'll get more talked about in later talk, that there's been widespread misuse, not by official mathematical statisticians, but widespread misuse by the scientific community of the p-value. And we at the Census Bureau think it's part of our obligation to help with the more enhanced or nuanced education of the scientific users about how to document the scientific validity of your inference. So one of the very nice features about the SIP synthetic data was not designed in on purpose. It was an accident discovered by myself and Ian when we were writing that first paper I cited. In the sense of Meng, the synthesizer is not congenial to most of the evaluation models that economists and demographers and sociologists like to run on these data. Those evaluation models are known as regression discontinuity models in the social science literature. That means the analyst says that something happened at a specific date, this date in this picture, which I'm not going to explain until I'm done. And before that date, there's a regression function on the running variable, which is a date or time to the change. And after that, there's another regression function on that variable. And there should be a break at a specified hypothetical time. The null hypothesis is that this non-parametric regression function shifted, intercept, and possibly slope at this red line, at the breakpoint. Okay? Well, you can prove that a regression discontinuity local average treatment effect is not identified if you've added noise to every single value of the running variable, and that's what happened when the data were synthesized. So this is the synthetic estimation of the model that was proposed by Marianne Bertrand and 2 of her colleagues, Emir Komenica and Jessica Pan. It was published in the Quarterly Journal of Economics. You're not economists, that's the top-cited journal in economics, in October, yes, 2015. So she gave this paper at Cornell, and she didn't have any of this analysis in it, and I said, you ought to run this model on the SIP synthetic data because you'll get 400,000 households and you'll get a really precise estimate of the break if you're right. So she went off and got her account. This was in November of 2012. She went off and got her account, and then she sent me this picture about a week later and said, there's nothing there. Send it in for validation. By the time of the AEA meetings, that's January of 2013, there's the picture that's actually in the paper. So, what was submitted for validation is the algorithm that specifies the non-parametric regression to the left and right of the breakpoint and the definition of the breakpoint. So that algorithm ran to do this on the synthetic data. It ran to do this on the underlying confidential data. There's a nice clean break right here. What was the hypothesis? that women prefer to marry men who make more money than they do, and the break point is where the household income contribution by the woman crosses 50%. So in the synthetic data, there's no real obvious break there. In the real data, there is a statistically significant break at 0.5, so the hypothesis is confirmed, and that's the only p-value in the whole paper that actually has the classical definition of a p-value, because they couldn't do any pretest specification. I've exhausted my time. I want,
John?
yes.
Could you go back to that picture on your exhausted time? So just the left half is, tell me what the left picture is versus the right picture.
Synthetic data estimation of the treatment effect associated with a break in household income at 50%, where the running variable is the contribution of the wife to the household income, so it breaks at 0.5. Okay.
On the other side,
Exactly the same analysis run on the actual data.
and the break is again at 0.5?
Well, the hypothesized break is at 0.5. You don't see it in the synthetic data because it's not statistically estimable in the synthetic data due to the way we did the synthesis.
Okay.
Okay? So it's as if you had published differentially private synthetic data where a particular high-order interaction was not in the model, so you had to ask that query. And when you got that query answer back, you could see that that interaction was important, and then the next time you do the synthesis, it's in the model. Okay? Yes?
Why did you say it was a, I thought you said it was a good thing that you're, you said we didn't know that we would have this consequence, that we made data, but it was fortunate.
So just like in drug trial analysis now, where you want the design of the trial to be registered in advance, and then you run the trial analysis on the outcome, and you have to put that into the public domain. You might not be able to get it published in a journal, but you have to put it in the public domain. If I have a public agency that wants to evaluate a program using the SIP, I would far rather have them specify the analysis on the synthetic data where that treatment effect is not identified, not estimable, and then have the community of interested scholars discuss how that evaluation was going to be conducted, essentially referee it in public, agree on the set of specifications that could be informative about the hypothesis, and then let everybody see the answer at once. And you can't do that in the normal way that people want to do. People want direct access to this, and then you don't see the search algorithm that got you there and then here. And it's a very legitimate critique of the way we do social scientists. So I'm as guilty of it as anyone else, probably more guilty than many of the people in this room. But it's a natural consequence of the way we did social science that we now have an opportunity to improve at the same time as we modify the way we're doing SDL. And that's essentially what I wanted to, that's my message. My last example is the American Community Survey. And the only points I want to make about it, I'll steal the 5 minutes that the projector stole from me, is that the American Community Survey, in its current publication format, so if you don't know what that is, that's the American micro-census that is run continuously between the full enumeration censuses. So it's always in the field, accumulating data. They are batched up and published once a year with a 5-year window used for the most detailed publication tables. Approximately 4 billion, not a typo, pre-formatted tables are stocked into the American Fact Finder. This includes the tables from the decennial census as well as from the American Community Survey for potential release. They've all been screened in the current SDL system. And a public use microsample is produced each year, okay? We would like to replace this with model-based estimates of the things that are in the publication tables, where the models are all formally private once we have fit them, and synthetic data with validation for the public use microsample. And the reason why you want to use the models is this is an example of what we currently publish. These are the 3-year ACS estimates from 2013. I should have put the attribution. This is the NCRN group at Missouri led by Scott Holen, who did this work. So if it's white, it means we didn't have data of high enough quality to publish there. And here are the margins of error, which you can see are generally in the range of 1,000 to 2,000. Using the published estimates, but with modern spatiotemporal models, we get an estimate for every geography. The geography here are counties, all right? And we get precision that's a whole order of magnitude smaller. So it's more comprehensive, it's more accurate, it's more useful. And this, once I sick a well-trained team on it, this can potentially be done in a fully private way. So we'll just gen up as many of these maps as you want after we've fit a sufficiently general model. That's Scott Holen's job. Scott Holen is also coming to the Census Bureau in the similar capacity to Jerry, and he'll be tasked with that. People already do this, but they don't use the differentially private or formally private publications. The New York Times publishes descriptions of New York City all the time that are spatiotemporal models, spatial mostly, of ACS data that have been improved by borrowing strength from the spatial correlations. It's a perfectly sensible thing to do, and we should do more of it. Okay. So I just want to acknowledge that my preferred form of this euphemism is that we have a long row to hoe. There's a lot of work to be done between now and being able to even have prototypes that we can show people for evaluation. But that's the work of the next couple of years. Thank you.
Thank you very much indeed, John. That's a really impressive prospect there.
All right.
I think we could take a couple of minutes aside since here.
So somewhere in the middle of your talk, you were talking about some things that had been done with formal privacy guarantees, but you said they weren't differentially private. So where's the gap? In what way do they fail to be differentially private?
So they're blowfish private, which I know means something to you. And so the blowfish graph is you're only a neighboring database if for the insertion or removal of an establishment that's within plus or minus alpha % of another one. Okay.
So if you had started with something that was differentially private, then you would have some kind of results for larger number of employees under group privacy, because differentially private is privacy automatically gives you group privacy.
Yeah.
Just not good enough for what you needed? You needed
So in principle, the global sensitivity is bounded, and that's unbounded. And even if we were willing to, so we used local sensitivity and smooth local sensitivity, even with the blowfish definitions, to get accuracy. All of our experiments attempting to get accuracy comparable to what we were publishing didn't produce anything acceptable. I don't think that's the best answer. I think the best answer to your question is I think that particular blowfish generalization will pass muster with the interested community when we try to discuss what it means to protect privacy and what is effectively a census of all the establishments in the U.S. So no one contests that their business is being used to compute these data. And the question is, before we were attempting to blur the distinction between establishments in an ad hoc fashion, and now we're trying to formalize what it means to blur the distinction in employment by roughly 10 or 15 or 20%. So, I think that an informed public policy discussion of whether that's a reasonable way to implement formal privacy can be conducted. And if you know, there's going to be experts on both sides of this now, and they're going to have the toolkits that you guys endowed them with. So if that debate comes down unfavorably, then we'll have to rethink that. But in the meantime, it's a much easier to defend way of doing what we were trying to do when we were using the ad hoc system. So that's my defense.
Okay, well, I think perhaps we should pursue it a bit later. I think we're in need of coffee, so thanks very much again.
You're welcome.